Hello, everyone, and welcome to the AI Club. My name is Uddesh Soman from Gen Engineering College, currently studying in seventh semester at Electrical Engineering course. Today, in our NLP session, we are going to have a look at Spacy and Gensim. So these are pre-trained NLP pipelines, NLP models or pipelines, we can say. So we will see how these pipelines are used for text processing, text prediction. So this one is just a short demo about using Spacy and Gensim. So let's start. And before going to Spacy, let's have a look at a couple of attributes that we are going to look. Dot text. If we create a Spacy model and pass, first of all, we'll have to import Spacy. We just simple command import Spacy, and we take our training data. We'll get to the training data later on. We'll just go with some simple examples right now. So we have we create an NLP object. This object is our Spacy model created using Spacy.load method. So dot load method takes in the pre-trained Spacy models. You'll have to download these models actually. So Core Web SM is one of the popular Spacy models that is available online. You can simply run a command in your command line, or maybe download it from the uh, Spacy's website. So once you have downloaded this model, you can load the model using Spacy.load. This whole thing is a pipeline which does couple of steps on your text. What are those steps we are going to discuss later on. Right now, just to give you a glimpse of what a Spacy model can do, let's have a look. So here we have this sentence. Tesla will start selling cars in India next year. Government says Elon Musk, CEO of Tesla, is now the richest man in the world. So this small ample sentence that we have here, we pass this text through our NLP object, the NLP object that we created earlier at this step. U just stands for unicoded string, just to avoid any conflictions regarding the coding, regarding the encoding of string. In a raw string would work the same. So once you have passed your sentence through NLP object, you get something known as this doc object. Doc object can, simply speaking, doc object can be imagined as a list containing each and every word that is present in our sentence. Like doc object would be like a list, not a list, but like a list that would contain all these words: Tesla, will, start, selling, all these words, and couple of properties or attributes that come along with it. So what are those attributes? We are going to take a dive into that. So before showing you that, I'll just go through a couple of ones. So dot text is one attribute that we are going to see. Dot text will give you the root text or the original word that was present in your sentence. If you call dot lemma underscore would give you the base word form of the word. Like if we have a word running, then the base word is run. That you can get using dot lemma underscore. If you just type dot lemma, that would give you a vector or a huge number. That number actually represents a certain word in the language dictionary of Spacy. So if you want to get the base word, you go with dot lemma underscore. We have dot pause underscore that gives the part of speech. Again, if you just go with dot pause, it would give you some vector number that means some word in that language dictionary of Spacy. But just for the sake of simplicity, let's just go with dot pause underscore. That would mean part of speech. So it is noun, verb, it is adjective, adverb, all that kind of thing. Dot tag underscore, that would give you tag of that part of speech. So if in case you want to do part of speech tagging for certain purpose, it will give you tags. Like if you have a noun, it will return NNP, and if you have an adjective, it would return ADJ. It's like that. Dot shape. Dot shape is actually the shape of your word, any word that enters in your word. So whether they are capital words, they are punctuations, digits. So this X stands for capital word. Smaller means the string has smaller case characters, then we have digits and punctuations and so on. So that the shape of your word that can be obtained using dot shape underscore is alpha. So alpha characters, if your token is an alpha character, so whether it is that's just a binary value, so it returns boolean true if it is an alpha character. Is stop, so is token part of stop list. So stop list actually comprises of stop words. So if you have gone through the theory section of this course, you will know what stop words are. Stop words are simple words that are usually present in a sentence, like is, the, return, and, can, but. And these kind of words actually don't contribute much to the sense of, don't contribute much to the uh, information in sense. Like if you are extracting noun chunks like Tesla car, Tesla India, or like say anything, uh, is MR, was, were, these kind of words are not something you require. So whether it is a stop word or not, you can find it using this is stop. So if it is a stop word, it will return true. If it is not, it will return false. Span, you can imagine when we have a list, we can slice the list, right? We can slice the list into certain fractions. Instead of having the whole list, we take a part of it. So similar thing we can do with doc. So a span is basically a portion of that doc object. Doc object is list of our words, and you take a portion of it, that gives you a doc object. So we just create two indices, starting index and stop last index. So whichever index you want to iterate to, -1. Same logic that goes with Python lists. Whatever be your stop, one index before that. So in case you start one and put stop is equals to 5, you'll get 1, 2, 3, and 4. 5 not included, means last index not included. Similarly, we have sentences. So if you call doc sents, you can segment your doc object into various sentences. Because sentences, simply because they are separated by punctuations like question mark or full stop. And if you split using those punctuations, you'll get doc sentences. Means you'll slice your doc according to sentences. We'll see that later on in today's session. So earlier we created our NLP object, this N-core WebSM model, that we loaded it using Spacy.load, and this is our NLP object now. We pass our sense, and now we can, since this is basic language processing, we can check couple of characters from sentences. So we iterate over the doc object. Remember, doc object is like a list, so you can iterate using any variable. So we call a variable token and iterate it for every item in doc. So for every item, print the text. So text attribute size 12, so 12 positions actually, and part of speech. The dependency we'll see later on, when it would be better to explain using visual aids. So there are a couple of visualization tools that come with Space. So dependency would be clear there. And dot lemma underscore. Dot lemma underscore will give us the base word. So if you see the output of it, we get Tesla, we find out that Tesla proper noun and it is n subject. So maybe so as the sub, it is treating as the subject of the sentence. So kind of like that. These dependency tags actually you will have to check out the documentation and to understand the meaning of these dependency tags in case you want to use it somewhere. Otherwise, just for the sake of completeness, we can see the dependency tags and the lemma. So Tesla is a noun, so lemma is obviously same. If you see as selling, selling is our verb, and we can see we get the lemma as sell. So this is the root word. So dot lemma would actually give us the root word for any word, and it does that for the whole sentence. Now, from the training data that we imported earlier, our training data is basically bunch of sentences. So we take all the sentences, we split them. Actually, these are sentences with positive feedback or negative feedback opinions. So whether some sentence is positive, so it would be the target attribute of the sentence would be one, and we take the text out of it. We take the text column out of it. So our text column is our deeds are the reason for earthquake, forest fire. So these are, I think, accident tweets about accident and all. So just we'll just get through those and target zero. So whichever are neutral tweets. WhatsApp man, Lala Food. So tweets like this. Now uh, we need to check the pipeline of NLP. So as I said, I will get to the pipeline of NLP. So these are the uh, this is the whole NLP pipeline, all the components that are present in your Spacy model. So we have token to vec to actually convert our token into vectorizer. I'll show you vector later on. Tagger, this actually gives you POS tagging. Parser, parser, uh, parser actually forms dependencies like which word connects to which word. Attribute ruler finds out grammatical rules between words. Lemmatizer, we get lemmatization to call the lemmatization. Lemmatization, we've seen getting the root word out of any word. And NER, named entity recognition. So named entity recognition is identifying the named entities like Tesla, Elon Musk. These are named entities. So their identification comes in NER. If you this was a NLP.pipeline actually gave us a list of tuples with named entities and their object types. If you just call NLP.pipe names, you can see the name of each and every component of the pipeline. So again, we pass a sentence through it. We pass the text. We have an example sentence here. We pass it through NLP just like we did earlier, and we get our doc object. From that doc object, remember, we can create a span. Span is basically a portion of our doc object. So we create a span from 30th index to 50th index. We can print the quote. This is our quote. And if you see this, the type is actually Spacy token span. So this is actually the type of your document span. If you slice the document, you'll get a span. So let's see what else we can do here. We can, if you remember, we can call dot sentences, dot sents to break into sentences. So we take sentences for I in send. So will just enumerate for doc send. I in sentence enumerate doc send. So what it will do is actually break break the whole text into various sentences, and once they are broken into sentences, it will print each and every sentence. So here you can see, yeah, we get each and every sentence. Now, if you want, you can either iterate over whole doc object, or you can take the entities out of it. Entities actually make it easier to do the work. So for entity in doc ents, so dot ents would return you entities. Entities means each and every token. So that we take the list of each and every token, we pass it to the variable entity, and now we can all those methods that were all those attributes that were applicable on the token are also applicable on entities as well. So dot text would give you the main text or the original text. So we have Elon Musk. Oh, sorry. I apologies. Dot ents will actually give you named entities, not the whole sentence, but only the named entities. Whatever named entities are recognized. So if you want to the named entities, we call dot ents. Dot ents would actually pass would actually take the result of named entity recognizer that we have seen earlier in the pipeline. The named entity recognizer that we saw earlier, it will take all the entities it recognized from that, and entity text. So whatever be the original text of the entity. So here we have Elon Musk. Entity label. So what is the label? So named entities are actually labelized whether someone is person, organization, it is monetary value, it is geographical position, or maybe some numerical value. So all that named entity recognizer can recognize this. So entity label. So here you can see on Musk entity label person, and you can check what is the explanation of that entity, means what that entity means. So in case you have problem reading these entity tags, we can just call Spacy.explain. Spacy.explain would create an explanation for those entities. So entity label, we pass the entity label, Spacy explain, we convert it into string and then print it. So if you see person here means people, maybe fictional. ORG stands for companies, agencies, institutions, etc. Organization. This $189.7 billion, it is recognized as money. So monetary value, including unit. This Jan 8, 2021, this is recognized as date. So absolute or relative dates or period. So you can get named entities or all that out of it using Spacy. And remember, all this we are doing on a single sentence that we pass through our NLP model. All this we are doing on this sentence. We only passed it through our NLP object that we created earlier. This is just the Encore Web SM model that we are using right now. Now we have noun chunks. So noun chunks. So if you remember chunking basically means grouping similar entries together. So we using Spacy model, we can check the noun chunks. So noun chunks here we get through dot noun chunks. We call dot noun chunks on our doc object, and we can print each and every. So that what we'll get is basically a list of noun chunks, and we can iterate over that and print the text that is present in that chunk. So all those noun chunks are Elon Musk, the billionaire CEO, Tesla, SpaceX. So these all These are all noun chunks. Next up, yeah, built-in visualizer. So if you remember, we were going to talk about dependencies. So we can see the dependency uh, dependency plot. So which words actually depends upon which, what relation do words share among each other. We can see that using Displacy. So Spacy has built-in visualizer known as Displacy, and from Displacy we call this render method. Render method all needs a doc object. Doc object means your the document or whatever the sentence you have passed. Style style DEP stands for this dependency graph. Jupyter equals to 2 to create this inline display in Jupyter if you are using Jupyter Notebook. Otherwise, if you are using Python VS Code or anything else, it would I think it would give you an image or something like that. And option is for additional settings. So here, though we have set distance is equals to 90, so separation between words. So separation is for 90 pixels. Distance actually stands for separation between entities. So each entity is separated by 90 pixels. And you can see which what is the dependency of this space is actually just blank space. We start with Elon. So Elon and Musk are related. You can see there is dependency between Elon Musk is this is actually reflected here. The billionaires, the billionaire CEO. So CEO is related to the and billionaire, and Musk is related to CEO. So Musk, since Elon Musk is the CEO, so Musk is the CEO, followed by off, then Tesla and SpaceX. So Tesla and SpaceX are related, and they are connected by this conjunction. And so all these kinds of dependencies that exist, you can see using Displacy. Earlier, we saw the dependencies in the form, what kind of dependencies they have in the form of list. So word followed by its dependency. We can also check the parent for that dependency. So we'll get which word actually relates to that dependency, which word actually creates that dependency that we can do as well. So this was built-in visualizer. We have entity recognizer. So the named entity recognition that we did here is actually quite uh, not very visually appealing process because you get a list and you do not have your whole sentence to reference from. Rather than that, we pass the whole sentence through Displacy render, and now we change the style to ENT. ENT stand for entity. So it would run entity recognizer, named entity recognizer, and you'll get your named entities highlighted. So if you see here, you have your whole sentence, and all the named entities are highlighted with uh, with what kind of entities they are written next to them. So Elon Musk person, Tesla organization, Amazon organization, Jeff Bezos person, and this 189.7 billion, this money, Forbes organization. So all the named entity recognition works. And this one actually, personally, I prefer this kind of visual representation for named entity recognition. So that is also available within Spacy. Once you have passed a sentence through Spacy model, you can do all these kinds of things with that word. Now comes stemming. Stemming inherently is not available in Spacy. Stemming, but in case you want to do stemming, stemming is available in the NLTK library. So stemming basically is a simpler form of lemmatization. If what lemmatization does is gives us root word. Stemming actually cuts short on that thing. It cuts out the suffix or prefix from that word. Stemming has the ability to identify suffix or prefixes, and instead of converting the word to root word, it cuts out the it cuts out suffix or prefix. So if you want to save time, stemming is efficient. Stemming does not take much time for processing. Stemming gives you words, and if your data set has enough information, that stemming won't be a problem. Like, because if you see here, fairly is a word, but it removed uh, y from that and became fairly, and ran remain sm easily. It removed y and I added I for some reason. So all that stemming actually creates wrong words, means wrong spellings, and different spellings can cause words to mean different. So stemming, though not preferred, but in case you want to save time, and instead of because lemmatization actually converts into root words, so it takes some time to process. Stemming is rather quicker process. So if you want to do that, that can be done using the NLTK library. And from NLTK library, there are multiple stemmers available. So one is Porter stemmer. We can import it from nltk.stem.porter. We take the stemmer, we have a bunch of words. We can simply pass our words through the Porter stemmer. Porter stemmer is pre-trained for that. So we create an instance of Porter stemmer, and we call the method stem on word, each and every word in this list. So you can see run remains same, runner remains same, ran remains same, runs. So from runs, it removed the uh, uh, suffix s that makes it plural. Easily, it removed y and I added I for some reason. I don't know. Fairly, it removed y, again added I. Fairness, so it removed any double s and the word remains fair. So that's how stemmer works. If you There are multiple stemmers available. Multiple stemmers actually generate different kinds of result. Not all stemmers have the same result. So instead of Porter stemmer, if you want to use, there is snowball stemmer. Snowball stemmer can also be used. Snowball stemmer actually comes with multiple languages as well. So we have to select the language actually before beginning. So we start with English. That's what we are using here. We have the same list of words, and we iterate each word. We call the dot stem method over the word, and what we get is run becomes run, runner remains same, runs become run. Easily, again y removed I, but if you see here, in fairly, it kept the root word fair. It just simply removed ly instead of just removing y and adding I in earlier case. So you can see this difference in result, and if you use multiple stemmers, you will encounter various results. So in case you are using a pipeline and if you want to choose from multiple stemmers, I'd recommend uh, use uh, use different stemmers and just go with one that gives you the best result. Also, just to add one more comparison of how different stemmers work. So here we have words generous, generation, generously, generate, and we pass all these words through snowball stemmer and also to Porter stemmer. So you can see snowball stemmer actually keeps most of the generous remains generous, generation, generate, it removed ion, and generously, again we get generous, so that's good enough. Generate, it removed e, so we again have generate. But Porter stemmer simply removed all the suffixes OUS, Asian, Asli, 8, and all we are left with is genus. So again, by this analysis, I would say snowball stemmer is better. But honestly, if you want to check for yourself, if you want to use it in a pipeline, I'd recommend check for various stemmers, and whichever gives you the best result, go to that. Bet or better, if you have better computational resources, then I would recommend instead of stemming, go for localization, because root word, keep having a root word would make much more sense. So again, we take a sentence. Now we'll have a particular example of lemmatization. We take a sentence. I'm a runner running in a race because I love to run since I run every day. This is the text we have, and we pass it through our NLP, that is Spacy model and Core Web SM. Passing it to NLP would give us our doc object, which would contain various tokens. So we iterate over these tokens, and we can call dot text. Dot text would give us original text. POS underscore, so that will give us POS text. Token dot lemma. Here I wanted to show you. Token dot lemma would give you a vector ID of this kind. This is some ID for a particular word in Spacy's dictionary. Spacy's dictionary means Spacy's dictionary digests each and every word that it encounters and assign it a separate number, separate ID. So that dot lemma will give you that. And if you called dot lemma underscore, it would give you the root word. So the example is pretty simple. Now we move on. Stop words. Yeah, coming to stop words. So stop words are words that are frequently found in our sentences. They may be determiners, connectors, conjunctions, but again, they are not important words in a sentence. While while doing natural language processing, most words are not important in many cases. So stop words actually, we prefer to remove stop words most of the times. So what are the stop words? We do not have to actually go through the dictionary and get to stop words ourselves. We stop words are already available in our model. So here we have loaded model again. We can just call dot default stop word. So default stop word means all the available stop words that are in dot our NLP object. So this is the list of stop words. We can call we can call length. So to check how many stop words. So by default there are 326 stop words. If you want to add more stop words, we'll see that in a second. So if you to find out whether a word is stop word or not, we have earlier seen this is stop attribute. So here we are going to use it. We have a couple of words, is, and, Tesla, you, is, and. So whether a word is a stop word or not. So we iterate over each word, and we take the word out of vocab. We take we need actually the vocabulary of that word. So we take the word, we find its vocabulary. So that would be the vector that we have seen earlier, and whether it is a stop word or not. So that is a stop word. So true is a stop word, and is a stop word. True. Tesla is not a stop word, so this remains false. You and all. Now, just imagine for a case there are internet slips that are not available in this list. You want to add them. Internet slangs, short forms that you want to be considered in stop words, but currently are not there in the above list. So how to add them? We can call default stop words, nlp.defaults.stop words, and we can call add method. Add method would actually add your whatever word you pass to the list of the stop word. So here we have added btw and this u. BTW is actually internet short form from between, u for Actually, YOU, instead of writing the whole word, we just go with you while writing text. So here we have sentence. Where was you? I was looking for you between sessions. So we have this kind of sentence. We split each and we call dot split, so that would actually split each and every word, and then we can iterate over these words. So whether is stop, whether it is a stop word or not. So to print true or false, we just call is stop on vocabulary of each word. So if you see here, we have added you here. So you became a where and you should be stop word. I think there must be some error with the function. Since we have added the stop word, it is a stop word now. If you see, BTW was added. BTW actually became the stop word. I think there must be some error with compilation running. If you rerun this, maybe you will be added. So this actually worked for between BTW. So BTW is a stop word and it recognized it as true because we added BTW. Next up, we can remove a stop word. So in case whether you want to remove certain available stop word of all these stop words, 326 stop words, if you want to keep particular word and not make it a stop word, then we can go with this. We call the NLP.vocab and again is stop and we assign it false. False means it is not a stop word. So sentence, again we have the same sense. We check whether it is stop word or not. So if you see here for, now for is not a stop word. Earlier it was a stop word. So that's how you can add or remove stop words. It didn't work for you, maybe for some reason, but it worked for BTW. In most cases, it will work for each and every word. Now, phrase matching. So phrase matching, basically, couple of phrases actually mean the same. So whether we can have multiple patterns and we can call phrase matching on those. So here we have our matcher object. Matcher, we call NLP.vocab. We pass our whole vocabulary into this matcher object and we add multiple patterns. So to decode this pattern, we have a list of all the words that are in our pattern and a dictionary. So in lowercase, solar power, this kind of dictionary, lowercase solar power. So solar power. If you wanted it to be in uppercase, you could have written UPPER. Here we are just going with default means lowercasing everything and then processing. So just writing lower would again we if you want solar dash power. So lowercase solar, one punctuation term. We have not specified which punctuation, but any punctuation term. And so true means the solar is followed by any punctuation term and then power again in lowercase. And two separate terms, so lowercase solar and lowercase power, each in their separate dictionary. Now we can list up all these patterns. So we create a list of all these patterns. We pass a string. So maybe which phrase all these patterns relate to. So if all these patterns relate to the phrase solar power. So you have passed solar power as a phrase. We could have passed solar dash power or solar space power. That wouldn't make a difference. That would all be same. So we call matcher add. So this solar power actually going to be a vector. So this vector, the out in our output, this vector actually comes from solar power. We have a text which considers solar power in all three forms. We have solar power created by space. We have solar power whole word and solar dash power in our sentence. So it would identify the phrases and would give us the location of phrase. So we again create doc object from our text. Then we pass that doc object to matcher, the matcher object that we created earlier, vocabulary. And we print all the found matches. So this one here is actually the vector for this phrase solar power for original phrase. Then these 1 to 3 and 25 to 26, 33 to 36, these are the position of your phrases. So since there is space, so the space is include 0 and solar starts with 1. So first index solar, then power. So solar power 2 words. So because if you remember in indexing, last index is not included. So we have +1 index 3. Again, solar power here is a single phrase available at 25th index. So 25th and +1 index, so 26 end index. Starting index 33 for this, that is solar dash power. So starting index 33 and ending index 36. So this is how we can match phrases. Now we come to word vectors and semantic similarity. So we can check when words are similar, words or entities or tokens are similar to each other or not, and to what extent they are similar. So the extent is actually 0 to 100. You multiply it with 0 to 1. You multiply it with 100, you'll get it in percentage. So what percent of similarities between two words or two entities, we can find this. So for that, we'll need Encore Web MD model because Encore Web SM does not support this. So we have Encore Web MD model. We import this model. Instead of making Spacy load, we can import the model and caught load method on it. To it is similar to writing Spacy dot load. Now we have two documents, and it is as simple as that. We can just use this method dot similarity with which. So we can do this for sentences, we can do this for document spans, we can do this for single tokens or multiple tokens as well. So I like fast food, I like pizza. So what is the extent of similarity between these two? So 0.86, 0.8698, so 86.98%. If you and because since we only have two doc objects, so obviously whatever doc 1 has the similarity doc 2 would have the same similarity with doc 1. So the similarities actually have same values. Now we can compare two tokens instead of two sentences. So we take pizza and pasta out of this. So pizza is at second index, pasta is at fourth index. We take second and fourth index, check the similarity between these. So pizza and pasta, not so much similar. 0.6, 0.6850 similarity. We can do it on span. Span means a portion of sentence. So from second index to fifth. So second, third, fourth, fifth not included. So second, third, fourth. And we have another sentence. McDonald's sells burgers. We pass both these sentences through NLP. Check their similarity. You can also check dot similarity span. It would give you the same result. So 0.471. We can also see token tags and call the explanation. So earlier we have seen dot explain to see what the named entity tags mean, we can call dot explain on any attribute of our doc object, tokens in doc object. So since we have this sentence, since Mass wealth has grown almost tenfold up a staggering $163.1 billion. So we take the doc, we create a doc object, NLP text. We pass our text to NLP, so we get the doc object and iterating over each token. And here we call the explain on token tag. So what kind of uh, tag we have? Uh, these are tags. These are actually tags for that. These are actually that POS tags. So part of speech tags. Since this one is IN, we printed. We will get the main text, the POS tag. What is that tag? So this one is actually additional tag and Spacy explain. So SCONJ. So we also have a blank space here, so that ended up as space. And we take its explanation. So POS tag and what is the tag of word? So RB actually stands for adverb. We have adverb here. RB again for adverb, punctuation, comma, it's a punctuation, and its explanation is punctuation, comma. And you can see this for the whole sentence, the each and every word of the sentence. So that is how you can use dot explain. You can use it to understand these tags. If you can go through, you can either go through documentation and read about these tags, or you can just call dot explain if you want to make a quick analysis. Next up, part of speech tags. So coarse grain means uh, uh, more like on the surface. So adjectives, adverbs, adjective, adposition, adverb, auxiliary, conjunction. So these are all part of speech tags. There are also fine-grained part of speech tags. So affix, adjective comparative, adjective superlative. So degrees that degrees that come with adjectives. Adjective predeterminer, pronoun possess. Even if it is an adjective, it can act as a pronoun, possessive pronoun. Determine. So these are more finer tags, and they are also available in our dictionary or Spacy model. By calling dot tag, you can get these finer tags as well. So we can see how to work with POS tags. Just simple demo. So we take any sentence, pass it through our NLP object. We can take any token out of it and print it. So we have read. Read is a verb. Its tag is VBD, and so VBD would not only give us verb, but the tense. So VBD stands for verb in past tense. So I read a book. I am reading. So reading actually becomes verb. VBG, that means verb. Gerund. Gerund means ending with ing or present participle. So it is either a word that ends with ing or represent present participle, or present participle meaning present continuous. So next up we have counting POS tags. So we can have a count of POS tags as well. So dot count by. So another sentence, the quick brown fox jumped over the lazy dog's back. So we have we get the doc object by passing through NLP, our Spacy model. We have POS count. So we call this method by on our doc object count by Spacy attributes pos. So Spacy attribute pos would return POS attributes, and uh, based on those POS attributes, we can make count. So we get POS count. We create a new dictionary, and for key value in POS count dot items. For each item, we for with that text we create a key and value. And if we print it, we have 90. 90 stands for determiners, DET, and we have two determiners. This 84 stands for adjective. We have three adjectives. 100 stands for noun, and we have one. So that would actually take from the vocabulary, because in vocabulary, all these words are represented by some numbers. So determinants are represented by 90, noun by 100, adjective by 84, verb by 85. So these are actually numerical representation, and we can, by calling vocabulary key dot text, that would give us uh, that would give us the actual POS tag in the form of text. Now we can move to Gensim model. So for unsupervised topic modeling, natural language processing, we have this Gensim open source library. It also contains preloaded models, pre-trained models. So, and for uh, plus for having text set or text data, we will be taking here Pride and Prejudice, the novel written by Jane Austen, and we'll treat it as our data. So we take Spacy again. We load the Encore WebSM model. We read the file. That file, you can download this file from the given link and read the file. If you have this file in the same directory as your Jupyter notebook, then this simple code would work. Read file name. It would open with read tag encoding UTF-8. UTF-8 simple encoding that would prevent any kind of glitches or any kind of exceptions later on. And we just call the read file on sample text. Sample text is actually the name with which I stored it in my directory. And process text. So NLP text. Whatever text that we gained by reading. So the whole Pride and Prejudice novel, that is now our doc object process text. Checking for sentences. So earlier I've seen dot sentences. Dot sends would return us a list of sentences. So we take that list of sentences. So we call dot sends on our doc object. Process text here is our doc object. And as far as in process text, so that simple list continuation, we'll get the sentences. We can check there. We have 4 sentences. And if you want to print couple of sentences from this list, so we can print couple of sentences here. So from 30th in sentences that are from 30th index to 34th index means 33rd index, if you not including the last one. So we get sentences. We take text out of process text and split it. So we have some 1,24,749 words. Now we see word to vec. Word to vec is the main thing that we wanted to see in Gensim model. So word to vec actually creates vector for each and every word in a sentence, and you can actually control the dimension of each and every word. So we have the sentence, process sentences. Remember, we again create a list of process sentences. So sentence dot lemma dot split for sentence in process text dot sentence. So process text dot sentences would return each and every sentence. That sentence would we'll take the root word or the lemma out of each and every sentence and split. Split means since they are in sentence, we will split them in words, each and every word. So we'll get a list of this kind, and each entry in the list would be a sentence or another list, a nested list, and each nested list would contain the sentence in this form, each and every word separated. So the project Gutenberg of ebook list is our first sentence. There are multiple sentences like this. So each sentence is now of this form. All those sentences are together in together in a bigger list. So now we pass this list list of words. So list that contains list, and each list contains a sentence. We pass this to our word2vec model we imported earlier. Minimum count. What should be the minimum minimum count or minimum number of sentence that we require? Size is the size of vector that we need. Size of each vector that we need. So we can adjust the dimensions. So here we are opting for a vector of dimension 200. So each word would be represented by 100, a vector comprised of 200 numbers, 200 different numbers. Window, minimum number of words in a sentence to be included. Compute loss, that would compute loss, training loss at each step, and SG, stochastic gradient. So with coefficient 1. This whole command would actually train the word2vec model. We can check the vocab. So what is the vocabulary of that? Training loss. So to print the training loss. And now that we have trained our model, we can check the similarity with different words. So for W, sim in interchangeable words, word vector, our model, we code vector on that, and most similar method, and most similar to this string, the provided string. So most similar to the string Darcy. So which words are most similar to Darcy? So that word and the extent of similarity. We have Wickham, that is similar to 98%, Bingley 0.97, Collins 0.95. So these must be the characters that frequently appear with the character Darcy in the novel, and that's why they have more similarity with Darcy. In case some word does not occur more frequently with Darcy, it would be less similar. So next up, we can evaluate a sentence. So we have another model, fast text. So again, in fast text, we pass our window. So minimum number of sentence, minimum number of words a sentence should have to be considered. Build vocab. So build vocab is the main training function. Build vocab is actually function to add your sentences. So corpus iterable is process sentences. Process sentences, we create the list of sentences we created earlier, and we call the train method. So we have again we have process sentences for the iterable corpus. Total examples is the number of entries that are in total examples, and 10 for 10 epochs. We'll train it for 10 epochs. Again, we call this similar method for the word Darcy. And if you see here, this fast text actually works better than basic word2vec model. because we can see now Darcy is the most similar word to Darcy, variations of Darcy. So Darcy exclamation mark, Darcy semicolon, Darcy question mark, Darcy comma, Darcy full stop, Darcy comma, this Bingley's, Darcy apostrophe s becomes. So now these are more similar to Darcy. So by default, we get top 10. If you want to check more, you can just go for top n attributes. So we as many number of the number you pass, that many results you'll get, which are similar to the provided word. Now we can also see what happens if we extend the window, means minimum number of words that should be in a sentence to be considered. So here we kept window 50. So again, build vocabulary, the whole step is same. Now that we check with us, since some of the samples are now excluded from our text, we can see the result is not that accurate because now Bingley has greater similarity with Darcy, which was not the case earlier. So this is how we can check various similarity between various text entries. We have seen the similarity. We have seen the similarities between text spans, sentences, or words with both Spacy model and Gensim model. And even in Gensim, we covered two models: word2vec and vec and fast text. So just to sum up for today we have seen multiple attributes that are present in Spacy. We have seen two Spacy models, Ncore Web SM and Ncore Web MD, how to use that. We have seen multiple text processing steps that we can do using Spacy. There are multiple natural language processing steps that are available in Spacy because of the pipeline that contains various components. We get the doc object, and we can practically do most of the text processing, text identification, text analysis using Spacy. So we have done all that. We have done named entity recognition, noun chunking, in visualizers. What are the visualizers that are available in Spacy to check your uh, check your sentence, the relations, named entity recognizer. Then we have seen the process of stemming and lemmatization, how it is done, which one to use better. We went through stop words. So what are stop words? Stop words that are available in a model, and how to customize the stop words. So whether to add or remove a stop word, and phrase matching. And the last but not least, we went to similarity. So we check the similarity of sentences or phrases or entities using Ncore WebMD, followed by we saw a brief demonstration of the Gensim word-to-vec model that included that checked for similarity for the word Darcy on that Jane Austen's novel Pride and Prejudice. We can do that for any data set, of course. And later we saw the fast text model that's also available in Gensim library. So thank you. That's all for today. I hope you have enjoyed the session. Thank you very much.